Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the fluid velocity and the flow rate. For an isentropic flow in a duct such as a ladle, the energy equation is. From this equation, the velocity and the outlet of the duct is. For ideal gas, we have the outlet fluid velocity. Based on equation 9.5, we have another form of the fluid velocity. Substituting isentropic relation for specific volume and pressure to the expression. Finishing integration, we have expression for the fluid velocity. When the Mach number at the throat is unity, the properties at the ladle throat are critical properties. From equation 9.22, the critical velocity can be expressed as this velocity is the speed of sound at the ladle throat. From the stagnation state to the critical state, the flow is isentropic. We then have this relation. Substituting the isentropic relation to this relation, we have the critical pressure ratio. The critical pressure ratio is evaluated for various values of kappa and are listed in equation 9.25. The critical properties of compressible fluid should not be confused with the thermodynamic properties of substances and the critical point. The critical pressure ratios for some typical fluids are based on the critical pressure ratio. The critical velocity can be simplified as the mass flow rate can then be determined by definition as incorporating with the isentropic relation between the stagnation state and the throat. The mass flow rate can also be expressed as when the Mach number at the throat is unity, that is, the critical state is reached at the lateral throat, the mass flow rate is the maximum flow rate. Thus, the maximum flow rate by definition is expressed as combining with the critical velocity and the isentropic relation yield the final expression of the maximum flow rate. Thus, for a particular ideal gas, the maximum mass flow rate through a ladle with a given throat area is fixed by the stagnation pressure and temperature of the inlet flow. The flow rate can be controlled by changing the stagnation pressure or temperature, and thus a converging nozzle can be used as a flow meter. The flow rate can also be controlled, of course, by varying the throat area. This principle is very important for chemical processes, mechanical devices, flow meters, and anywhere the mass flux of a gas must be known and controlled. A plot of QM versus P2 over P asterisk for a converging nozzle is shown in figure 9.6. Notice that the mass flow rate increases with decreasing P2 over P asterisk. reaches a maximum and P2 equals Pc and remains constant for P2 over P asterisk values less than this critical ratio. To summarize, for all bank pressure lower than the critical pressure Pc, the pressure and the exit plane of the converging nozzle P2 is equal to Pc. The Mach number and the exit plane is unity, and the mass flow rate is the maximum flow rate. Because the velocity of the flow is sonic at the throat for the maximum flow rate, a bank pressure lower than the critical pressure cannot be sensed in the nozzle upstream flow and does not affect the flow rate. Okay, that's all for this task. Thank you very much and see you next time.